It's already recording, so good afternoon again. Sorry because today I only have one screen, so I have to be sorry. I have to be swapping between the slides and the Teams. Okay, so if you have a doubt, it's better for you to unmute the microphone and ask, because otherwise you will have to wait until I go back to Teams. Okay, so then the first question that you might already know is, what is a time series? Do you know what a time series is? Can any of you tell me something about a time series? Mhm. Yes, of course. A time series, it's data with timestamps. That is the key point. That all data must be accompanied by a timestamp. Okay, it are it's usually it's not usually data in the more how to say, I don't get the word for, it's like in the general way. Okay, it's not data in the general way, because usually in a time series we only have one value. Okay, so it's the evolution of a value during the time. We have observations of that value, maybe every day, every month, every year, and so on. Okay, but yes, basically it's data which comes with the time or a timestamp, of course. For instance, this is a time series. Here we have the how many nautical leagues Columbus navigated to in his first voyage to America. Okay, you see here that in the first day he navigated almost 10 miles, or well, not miles, but leagues, nautical leagues, sorry. The second day about 45, the third day 60, then 40, and so on. Okay, this is a time series. Now let's describe it. Can you say anything about this time series? Okay, I'm going to open also Teams on my phone so that I can also have a glance to the chat. Can you say anything about this series? Any trend that you may observe, or whatever? You can't see? Okay, wait. Sorry, I was checking the chat. But you cannot see any trend, right? Any of you? Okay, and I'm opening the chat in my phone, sorry, to have it. It has some spikes. Okay, yes. After its rest, he had a spike on speed then. Mm, well, but it's not actually, well, there are spikes, okay, but though those do those spikes happen suddenly? From Does it go from here to here in one day? it takes 4 days to change. Okay, and here again it takes 4 days to change. Okay, what I see is that actually, mm, even if we have some spikes, those spikes don't happen suddenly. Don't you think so? Or do you think that they happen suddenly? Yes. Well, I'm also going to say that I can see a trend here. My guess is that it is a trend which is a constant. Do you agree? Do you think that this is a constant? The trend is a constant? Yes, no, no? Why? I didn't get the question completely. Okay, here what I say is that the time series is constant over the time. That is what I say. Do you agree or not? Thomas says no. Why not? Mhm. No, no, constant in a mathematical sense. Constant means that it's always 30, for instance. Yes, but okay, now I'm going to say that it's more or less constant. Do you agree now? Maybe, yes. Well, in this case, the series is more or less stable, more or less constant. In average, the daily distance is about 30 leagues. For me, it is constant because we will see now in a couple of minutes that there are different components in a time series. One of the components is a random component that cannot be guessed. But we also can have a component which is a deterministic component modeled by a mathematical function, and here that component would be a constant function in, will, which would be a constant in 30. Okay, and then we have a random component which goes upper or more to the bottom, but it will be more or less constant. Okay, more or less related to what I said before, that the changes doesn't happen suddenly. For instance, here we go from here to here, but in 4 different days. This is also related to the fact that if a specific day he navigated a given number of miles, or sorry, of leagues, then the following day he will navigate also a similar number of leagues. Why might that happen? Because of the weather. Okay, the weather, well, sometimes it happens suddenly, but usually the changes are not radical. Well, sometimes it happens, okay, and moreover, depending on the part of the world in which you are, it might happen. But most of the times, it's a gradual change. It doesn't happen suddenly, okay? Therefore, well, we are not going to see that part because it's part already of ARIMA processes. But one observation of this time series is related to the observation in the day before. Okay, we can see that, of course, what I said, we don't go from here to here in one day. In one day, we have a similar observation. Well, there is some changes, of course. There is a change with respect to the previous day. Here we have a change more, a change, but they are in small steps. Okay? This one, what can you say about this one? Linearly increasing. Yes, it's almost linear. Non-stable increasing. Well, Dim says that it is not stable, maybe because of the last part of the series. Do you say that it is not stable because of the last part, in which the slope is lower? Well, I didn't say. This is the Spanish population over 16 years, from 1977 to 2000. Also because the average is constantly changing with each new value. Well, but that will always happen. The average will change constantly. Well, not exactly. Well, maybe when it is a constant or stable, it doesn't happen. But when we have a specific trend, as it is this case, it will the average will change all the time. Okay, but what matters here is, of course, the linearity. We can clearly see a linear increasing. Okay, it is not stable. It has a positive trend, a linear trend, what is more. Okay. And what I said, okay, here we have more a linear case, and then the slope starts to decrease. Well, here we have the number of births per year in Spain from 1946 to 2000. What can you say about this time series? This is a difficult one. What do you think? What can you say? Yes, of course. You're right. People had less babies after Franco. Yes, something like that. Yes, during these years, it happened what it was said, the baby boom. Like everybody were having more babies and more babies. But then, yes, more or less when Franco died, after Franco died, the number of births started to decrease. So here we have clearly two different trends in our series. What is more, here we have a different trend than here, but okay, here more or less it is stable, more or less. We could even say that it is stable here, then a little bit increasing, and then stable again. And then we have a clearly decreasing trend, but at the end, it starts to increase again. The series is not stable. It doesn't show a linear trend. It shows an evolutionary trend. The trend evolves with the time. Okay. Even here, we might think that it might be starting to increase again. What do you think? If you have to forecast a value for the future, do you think that mm, it will keep increasing after this? Is this the signal, a signal that the trend will change again or not? Knowing already what we know about what happened. Okay, it is not the starting of a of a hill again, because we know, yes, it will stay around 400,000, I think. Yes, because, well, actually, nowadays, even I'm not expert in demographics, sorry, but I think that it um, it is decreasing a bit. Going up in 2020 with the quarantine. Well, I don't know if more babies or more divorces, but yes, we will see what happens with the trend. Both, yes, maybe both. Okay, so that is a very difficult one. What can you see here? Monthly rainfall. Well, it is in Santiago de Compostela, which is in the north of Spain. It's a very rainy city. Uh, and what can you see? Seasonality, of course. Some months are systematically more rainy than other ones. Okay, for instance, I think that here in January, okay, because the year starts here, so this is January. It's more rainy. January. Well, here we have a strange thing. The mean is constant. Yes, the mean is constant. Sorry, the noise is less than before, but we still have noise. Okay, in real life, we will always have noise. Here, when we want to learn a model or whatever, we will always have noise. Okay, but yes, this is more, the series here is like more clear. We might not have that noise, but for instance, here in 1991, there is a strange point over here, because always in the start of the year we have here a peak in the graphic. Well, here maybe also, but always the start of the year is like more rainy, but sometimes it doesn't happen. Okay, but yes, we observe here seasonality. Okay, this is an oscillating series, and the average depends on the month. For instance, if you only represent as data the points of January's, you will obtain more or less a constant series. If you represent all the August, you will obtain another series, another constant series, sorry. And what about this one? What can you see in this series? There is noise. Why? Why there is noise? The noise are the peaks. Exactly. Hmm. I wouldn't say so. Any other opinion about this one? Here, what we have is a combination. It is increasing totally up to 1995. Yes, of course. If we consider only the series to this point, it is increasing. Here, it starts to get more stable. Okay, but of course, we have a trend, an increasing trend, not considering the last part. Okay, in the last part is still is sorry is stable, and it also has seasonality. Some months imply that we will have more gasoline consumption than other months. Well, I'm not expert and I don't know if they are January's or August's, but this is what happens. Okay. Okay. Clearly, this was like the boom of the cars. I think that in fact this series is still growing up. It's still a increasing series. This is something that happened here in these years, but I think that it's increasing. Well, maybe nowadays it is not with the coming of electrical cars and so on, but not sure. Okay, so we have seen already some examples of time series. I'm sure that you already knew some examples of time series. We have analyzed them from a graphical point of view. Okay, now we are going to analyze them with deterministic trends. Okay, what we want is to forecast the future values of the time series. For that, as I said, we are going to firstly use deterministic trends. Deterministic trends are those trends that can be modeled with a mathematical function, okay, and without seasonality. First of all, let us decompose our series in two components. We have on one side the level with game is asking general question: how would you deal with all time series that are going to contain a huge COVID-19 drop in the future? That is a very, very good question. It is not clear at all because, of course, we will have a very strange behavior during these months. It has happened, it is happening, and it will still happen for the next year. We are in times of uncertainty. If we go, for instance, let me see. Well, this is an economical index in Spain. If we see what happened in the last year, of course, and even if we go to the maximum, you see here that it falls from, well, here in March. Well, actually, if you see, this happened before already from February the 20th, it already started to decrease. And when the pandemic when the breakdown happened, it was already in the minimum. So maybe we could have predicted what was going to happen since February the 20th. Anyway, what will happen? How will we be able to predict? Well, I think that nowadays we can now predict, for instance, the behavior of this series. What was impossible to imagine was this. Of course not. We could not imagine this. But once it's back to the actual course of the series, I think that we can predict it again. It is starting to increase. I think that it will keep increasing. Well, actually, I don't know because let's see what happens with everything. We're in a quite difficult situation. I cannot say anything or on how to model these situations. Okay, there are things that happens with time series. Okay, we are not able to model everything. Moreover, well, we could have predicted using more methods, not only time series. For instance, we can combine methods of machine learning with time series. Okay, some approaches try to predict the behavior of the time series as a classification problem, because you already know classification problems, right? And maybe you can classify the behavior of the next day in the time series as to increase or decrease. For instance, classify. I have a classification problem, and I want to classify it the next day as going to increase or going to decrease. And then if it is going to decrease, it will be a lot or not a lot. Okay, and we can take more information that only the series by itself. For instance, we can predict the financial indices, the like this one, okay, and we can consider news, we can consider the decisions of politicians and so on. Okay, they are more elaborated approaches, not only taking into account the past values of the series. We are going to focus today in predicting, and usually time series approaches only use the past values of the series. But now they are starting to emerge approaches using more information, but they are very specific about the context. Okay, the methods that we are going to describe. Have you already done this prediction? Myself? About what? About the financial index or about what? No, actually my research is not about making predictions with time series. Okay. Well, in our group, Ernestina was supervising a bachelor degree project of a guy who did something about that. I don't remember what he actually did, but yes, he used news for trying to predict something about in the financial indices. Okay, I was in the panel of that work, but I don't remember exactly. It was something like that. Okay, it's not easy. It's not easy. Always time series are not easy. Okay. Well, going back to what we were talking about, of course, this is more basic. Okay, we can consider the time series as having two different components. Oh, no problem. Yeah, I'm happy to discuss always, because for me, as this is like a complimentary seminar for the course, I prefer if you have this kind of questions that we can discuss and think than just going through the theory. Okay, for me it's always better. Anyway, going back to this, if you have any question, of course, feel free to ask. Okay, we can consider a time series as having two different components by the moment. Okay, we will add another one later. What is called the level of the series and what is called the innovation of or the random component. The first component, the level, is a function of the time and some parameters, a parameter vector. Second component, the innovation, is a random component. We cannot take control on it. Okay, but we have to make some assumptions. The assumptions are that the expectation of of all the observations of the series sorry, is equal to 0. The variance does not change with the time, and the all the innovations follow a normal distribution with a mean of 0 according to the expectation and a standard deviation of the square root of the variance. Okay, and moreover we have to assume that two values of the innovations are independent if the instant of time is not the same one. Of course not. It means that the innovation here in a specific instant of time is completely independent than the innovation in other instant of time. Okay, they are not related to each other. Okay, so we are going to focus is here because the innovations we can do and we can do nothing with them because we assume that with the time the expectation is 0, so the innovations that are positive compensate those which are negative. Okay. So our objective is to try to forecast or to predict the value of the series at t plus k in the instant of time t plus k, given that we are now at t. Okay. A very simple model is this one. It has the trended series. It's a stable series, the constant series, just saying that the level predicted, you see here that we have like a hat on the mu. It means when we put a hat, it means that it is a prediction. Okay. Then the prediction for the level of the series is a constant. You remember that here we have time and a vector, a parameter vector. In this time, in this case, sorry, time is not present, and we only have one parameter, which is the value which is constant. Okay. In this case, the prediction of the series is the same than the prediction of the level, because actually it would be, let me write, it actually would be something like this. The prediction of the series would be the prediction, well, let me not to write the t plus k, okay, would be the prediction of the level plus the prediction of the innovation. But as the expected value of the innovation is 0, we can consider that the prediction of the series is the prediction of the level. Okay. Then as it is a very simple equation, any value in the future will be predicted by that same parameter. We can also consider a linear trend. In a linear trend, we have two parameters, and of course, now we have the time. Okay, it's a linear function. For instance, something like this. Okay, well, this is a t and this is a plus. It seems to be the same. Well, now if we want to forecast the value at k positions further, we have to substitute this t by the current instant of time plus the k positions that we want to go further. In general, we can model it with any kind of polynomial trend. They are not very usual, specifically the squared powers, okay, the polynomials of a squared degree, because when you have a squared degree, you will have something like this. They are not that common. Maybe when you have a degree of 3, maybe it's more common, but actually they are not common. Okay, the most common one is the degree of 1, the linear trends. Okay, and how to discover or how to find out these parameters? Okay, the parameters are found out using the least squares criterion. Okay, what we have to do is to minimize the sum of the square differences between the observed values and the predicted ones. Okay. As you already know, the predicted values is the same as the prediction of the level. We are going to do it with this series. Okay, in this series we have the observations 4, 6, 8, 13, 11, etc. Well, we are going to model it with a linear trend. We have that we need to minimize this. As we are in a linear trend, the level of the series is this. Okay, so we have this. Now we have to substitute the actual values of the series that we already observed according to the instant of time to which they belong. So if we go back to the series, we see that 4 was the first value. We are considered to that we are starting in 0, t, okay, zeta, sorry, z, 0 is 4, okay? So 4, e, 0, and beta 1 minus beta 0. The second value was 6, and in the t we write 1. The third value was 8 at t equals to 2, and so on, okay? If we perform all these calculations, we obtain a polynomial of degree 2 in two different variables, beta 0 and beta 1. We see here that we have 9 beta 0 squared plus 204 beta 1 squared plus so and so on, okay? Okay, we need to minimize this. To minimize a function in two variables, we have to do derivatives over the two different variables, and we obtain a linear system. When we are modeling a linear trend, we always get a linear system. Okay, this is which is easy to solve. We can also model some trends, for instance, with an exponential. But in that case, the resulting system will not be linear. Therefore, it will be more complicated to solve. Okay. Anyway, if we solve this very easy system, we obtain these values. Then the level of the series to model the series that we had before is this one. Okay. The next actual value is 26. What is the error if it was estimated by the use of this? Okay, look, let's calculate. Okay, so the next value is the ninth one, so it could be 41 divided by 15 times 9 plus 148 divided by 45. So the next value would be almost 28, 27.8888. Okay, so the error would be 1.8, more or less. However, deterministic trends have a big limitation. It is unusual for a real series to have a polynomial trend. Okay, we can try to model the series by intervals, trying to fit each interval in a linear trend. But in that case, for forecasting the future, we will have very few samples to forecast. So this does not happen. Does not usually helps. We are going to see more methods. Well, I'm also going to explain how to evaluate the goodness of a model, because it's not here. But let me see. Well, I'm going to go to Excel. And I'm going to write the series here. Okay, this is the instant of time, and this is the value of the series. Four, 6, 0, 8, 13, 11, 18, 20, 23, 25. Okay, I'm going to forecast the value. We can call this just seed. My prediction with a deterministic trend, a linear trend, would be, well, I cannot see the prediction could be 41 divided by 15 times p plus 148 divided by 45. So this is what we have. Okay, to evaluate how well these values represents the series, what we can calculate is the mean absolute error and the mean squared error. Have you heard about these metrics, right? Do you already know them? Then mean absolute error and mean squared error? Yes, of course. It's just, for instance, here I'm going to write seed minus seed spread actually the absolute value. I'm going to write the absolute value. Okay. So this is the difference in absolute value, and the mean absolute error is the sum of all these values divided by the number of elements. Okay, and here I'm going to write the squares. And divided by the number of elements. Oh. Okay. And these values does not mean anything by themselves, but they can be used to compare different models of the same series. Okay, always a lower error means that the model is better. Now let's move to exponential smoothing. I don't know if you have seen exponential smoothing in the course about time series. Have you? No. Okay. So actually, exponential smoothing is a very useful because okay, deterministic trends are not used in real applications. Exponential smoothing it is. Okay. What this method does is the following: is to combine the last prediction with the last actual value. It's a linear combination, okay? A linear combination in the sense that here we have zeta, and here we have 1 minus zeta. Of course, as we are combining our last prediction with our last actual value, we need to have here like the first observation, okay, because it's a recurrent equation. Okay, Dean is asking. I see that you are using Excel for calculating all. In my studies, I have not really used Excel. Could you say it is a good skill to learn from the data science field? It depends. You can do many things with Excel. Okay, I'm using it because actually they are like very silly examples. But I have also seen, do you know Banco Santander? Which is one of the biggest banks in Spain, and it's also in other countries of Europe. No? Well, it's one of the biggest banks in Spain, and it's also in other countries. I have been teaching some courses to employees in that bank, and they were using Excel for, I think that one of the employees showed me the Excel she had for clustering problems. Okay, you can do many things with Excel. For instance, you will see that here the time series I'm going to implement exponential smoothing on Excel, and it will be very simple to do it. Okay. But for other problems like classification, regression, clustering, I would use Python or R. Okay, Python or R are the most common frameworks. You can do some things in Excel. Usually, specifically if you want to do a quick check. Okay, for those cases, you might use Excel. But it's not that common, of course not. Okay, I hope that that answers your question. Well, here we have the equation for forecasting the next term. If we go one step back, the forecast of the current instant of time was the same, but here instead of having t, we have t minus 1. If we substitute this into the formula of the previous slide, okay, the formula was this. If we substitute the previous step, we have this, which is this, okay, and now we operate. If we operate, we will have zeta squared times the predicted value at t minus 1 and so on, okay. This happens if we operate. If we keep substituting the predicted values recursively, what we obtain is this. And here we have the reason why it is called exponential smoothing. Okay. First of all, if you remember, here we have like the initial value because it is a recurrence and we need a definition for the first value. The prediction for the instant of time 1 was the real time in the real value at 0. Actually, this value, which is a definition, okay, that is a definition. We could also consider this other, sorry for going back and forward. We could also consider this. You can do it, okay? Why? Because that first term is taken into account only here. That definition is only taken into account here when we elaborate more the calculus, okay? And what happens? Theta is a value, is a parameter of the algorithm. Okay, this is a parameter between 0 and 1. And it is elevated to the current instant of time. What happens? The current instant of time might be 100. Having, for instance, a value of 0.5 for theta, if we elevate it to 100, what is the actual weight of that first parameter? Almost 0. So that is the reason why the initial state doesn't matter. We can initialize it as the previous value or as anything that we want. Why we use the previous value? The value, the actual value of the series at the instant of time 0. Well, we use that value because when we have only a few terms, for instance 3, even if we have 0.5, it might matter, okay? Or even if we have 20, but the parameter is something like this, it might matter. Okay, sometimes it matters, but usually, okay, having a parameter of 0.95 is not that usual, because having a parameter of 0.95 means that actually this could be almost 0 and we would be predicting the next value as the previously predicted value. So we would have almost all the time the same value. Okay, but it might happen. Or even if it is 0.8, if we have 10 values, it might happen. But usually, even if we have 0.8 and we have 0.8 when we already have 50 terms, it's like nothing. Okay? And here what we have is this. It's the previous value plus zeta times the previous value plus zeta squared times the previous value, and so on. Actually, this is also multiplied here by zeta elevated to 0. So what we have here is a weighted average of all the previous values. If you see, these are actual values. Okay, so we have a why do we say that it is a weighted average? Because each of the values is multiplied by and so on. Okay, if we sum all these terms, considering it as an infinite series, this is a geometrical series. Okay, this could be the infinite sum. Well, it actually, here we would have n infinite. It could be this sum. What is the result of this sum? Do you remember from your calculus courses? When, of course, when theta is between 0 and 1. Do you know the result of that sum? Yes, I wait. No problem. But it's easier than that. Limit goes towards 1? No. 1 minus theta elevated to n plus 1. It's easier. Yes, I know that it's power. Well, actually, it's easier in this case. Okay, it is just the last part. Because I don't know if what you are writing there is a more generic case. Okay, in this case, it is just this. Okay, so yes, if theta is less than 1, which is the case, okay, because we are defining that it is between 0 and 1. So here we are multiplying by this. Then we put 0 for theta elevated to n plus 1. Okay. Yes. That was I said. That your answer was a more general one. I'm focusing in the case in which theta is between 0 and 1. Yes, of course. So the sum is 1 divided by 1 minus theta. And we are multiplying here by that term. That is why it is called exponential smoothing. Okay, it's an average of all the previous values, but with a decreasing weight, and the weight is decreased in an exponential way. The previous terms are exponentially smoothed. That's the reason why it is called exponential smoothing. Okay, it is the weighted mean of all the previous observations with decreasing weights. Okay, so let's see an example with the same series as before: 4, 6, 8, 13, 11, and so on. Okay, with a parameter of 0.1, we have these values. With a parameter of 0.2, we have these values. Of course, what you can see, okay, do you remember that the next value was 26, right? So we see that for this case, the closer the value to 0 is, the better. Why? Because this series was very well modeled with a linear trend. It is kind of this. And what are we doing with exponential smoothing? With exponential smoothing, what we are doing is just a combination between the last predicted value and the last actual value. Therefore, it is not able to increase the values. It is not able to model a slope. Okay, this works for another kind of series, but not for increasing or decreasing series all the time when they are increasing or decreasing all the time, because it can only oscillate. It can the next value, the forecasted values cannot be greater than the maximum that observed during the series. Okay, I'm going to code it in here on Excel. Okay, let's just take here the value of zeta, for instance 0.5, well 0.4, because 5 is not here, just to check that it is correct. And here the prediction. So for this cell we don't have a prediction. For this one we know that the prediction is the previous actual value. And here, if we go to the formula, it is the value of zeta times the previous predicted value plus 1 minus zeta times the previous actual value. Let me fix this and this. This is the result. Okay, this is for zeta equals to 0.4. You see, we can consider other values, okay, of zeta. Okay, so this method has the problem that I said. That is, it cannot correctly model when we have a trend, when we have a slope. For that reason, we can consider Holt's double exponential smoothing method. This method sorry, considers also a slope, and what is more, it considers as a change in slope. In this case, we can predict values which are not in the range that we have, because we are going to consider a slope and a value. Okay. What we have is that the prediction for the level is the sum of the prediction for alpha and the prediction for beta. The prediction of alpha is the smoothened prediction of the value considering the slope. Is the linear combination between the last previous value. Sorry, yes, this is the last, yes, and the previous value of the previous smoothing prediction plus the previous predicted slope. As you can see here, we are combining, or we are performing here a sum. Because of this, we can go out from our current range, okay? And we consider also the slope. The slope is considered as the subtraction of the two last smoothing predictions, okay? Because if we are here, these are the two last predictions, as yes, here. This is 1 because they are consecutive predictions. The slope is the increment in y divided by the increment in x. The increment in x is 1, so it's just the increment in y, which is this, what we have here. Okay, and we combine that new increment with the slope that we already had. Because sometimes, maybe if we only consider the new slope, we are including some noise. So to smooth the noise, we also consider the previous value of the slope. Okay, and initial values are these ones. Take into account that here we need 2 observations for predicting the slope. Okay, let's model this in Excel once again. In this case, I'm going to need alpha, beta, and then seed spread. And I have 2 parameters, theta and gamma. Theta and gamma. Okay. So alpha at 0 is theta at 0. Alpha at 0 is the first actual value. And beta at 0 is the difference between seed 1 minus seed 0. This minus this. Okay, and here we don't have a prediction, but we know that the prediction in the next instant of time is the sum of the previous alpha and beta. So this is alpha plus beta. And now the following alphas. Following alphas are theta. Well, I'll write a value for theta later, times the current value of theta, of seed, plus 1 minus seed, 1 minus theta, times the previous alpha plus the previous beta. And the prediction, well, let me fix this and this. And beta is the value of gamma times the subtraction of the two last alphas, the current one and the previous one, plus 1 minus gamma times the previous beta. Now I can move this and I can predict the next value. Oh, no, something is not working here, because the predictions for beta are not all the time the same. Let me check. Here, okay, yes, no, the problem is this, of course. I had not set the theta and gamma values. So, for instance, here we have an example of 0.2 and 0.3. You see that even if we could not reach or the maximum value that we had already observed in the series was 25, here we are reaching until almost 27. Okay, so that is the function of the slope, and moreover it is a change in slope, so it can not only model linear trends, it can model, it is a changing slope, because here we are considering the previous values, the difference between the previous value, the previous values. Okay, it is an adaptive slope, so it may model parabolic functions or whatever. Okay, let us represent these values, and we are also going to add these ones. Wait. No. Okay, and I'm going to add where can I here. Okay, you see that in the prediction, of course, as it was actually following a linear trend with some variation or some deviations, we see that in the prediction we can see that the linear trend is very well captured. Actually, even in those cases in which we have noise, the slope is not changed so drastically because it is smoothed, so that noise cannot be taken into account. Okay, even if we consider here, for instance, values which are with a quadratic component, consider that this is this elevated to 2, and it happens in all the cases. You see that we, of course, the slope increases, well, because maybe here 0. The slope increases not as fast and as the original one. This is not a real application, okay, but you can see that here we are also obtaining a quadratic function with the adaptive slope. Okay, So that's it. That's everything that I wanted to say today. Okay. I don't know if you have any question that you want to ask or whatever. Well, I wanted to talk also about seasonal series actually, but I didn't have time. Sorry, because as I were 30 minutes later, or so 30 minutes late, I didn't have for seasonal series. Anyway, I will leave these slides on Moodle. Okay, so you will have the opportunity to see what I was going to say about seasonal series, and you will see that they are quite simple to analyze from this point of view. Okay, so let me stop the recording.